So I'm going to talk about project that Leanne and I are doing with Jason. I'll be giving a talk about this at the Chesapeake Section AAPT meeting, which is the weekend after the March meeting. So it's about a week after the March meeting. And the setup for this, I'm sure all of you have felt this way. I know I certainly did. At some time in your physics career, for me, I think it was in my freshman year, but sometimes this seems to be taught in the junior level quantum mechanics. You have to deal with solving for the motion of a driven, dissipative, or just dissipative harmonic oscillator. And the standard way that it goes is you're told, instead of using sines and cosines, use exponentials. And you find that the exponentials involve either pure imaginary or complex numbers. And then you're told at the end, just take the real part because the position is real. That's almost exactly the way it was taught to me. You can do better with that, but I think it's a real problem with the way that we teach this particular material. And so I'm going to tell you about some new ways of doing it. It doesn't change any of the answers, of course, but it provides an interesting new perspective. And it even has interesting linkages with quantum mechanics, which I'll also point out before the end of the talk. Okay, so the title is Demystifying the Use of Complex Numbers in Driven Damped Harmonic Oscillators. Complex numbers are often introduced in mechanics as a tool to make solving driven damped harmonic oscillators or just damped harmonic oscillators. Usually, this is presented as a set of rules with an uneasy take the real part of the solution at the end. And in this talk, I'm going to show you a much more natural way to organize working with complex numbers in driven damped harmonic oscillators. So very interestingly, this starts from a textbook by Born and Jordan in 1930. It's a textbook about matrix mechanics. It was written in German. It was never translated because everyone had moved on past matrix mechanics at the time this book came out. And I have copied for you here, a section of the page in the book that talks about the harmonic oscillator. And you see it starts from the Hamilton equations of motion. Q dot for the harmonic oscillator is just P over the mass. And P dot, which is minus M times the spring constant times the position. You can combine these two together and get a second order differential equation that we're very familiar with. Q double dot is essentially minus omega squared Q. But what he says, or what they say, is form this linear combination, okay? And if you form that linear combination, what you find is B dot is a number. It's a pure imaginary number times B. And B dot dagger is the Hermitian conjugate number times B dagger. Now, these two differential equations are very easy to solve. They're just exponentials. And I'm going to show you where this comes from. This is the basic idea that they introduced. They then go on to talk about quantum mechanics and how you can solve the quantum harmonic oscillator. But they have this very interesting couple of lines on the classical harmonic oscillator. Now, if we look at a more standard approach, and this is from Feynman, the Feynman lectures in physics, when you set up the differential equation and you solve for the exponential, it seems like this must be I times the exponential, or minus I times the exponential. You get this complex result, and there are two of them. And if you put that together into the position operator, you see it takes this form A e to the minus gamma t over 2 e to the I omega t. And if you take the real part of that, for instance, take the real part, you see that you get something that's a nice real result. He then talks about taking the second answer, putting it together, and of course, you'll take the real part of this, and you'll get a general cosine with a phase shift when you do that. So that's sort of the standard way that it's done. From my perspective, certainly when I was a student, I found this to be very ad hoc. It wasn't well motivated. It was just like, here's a neat thing, let's go do it. And, there are these other steps that you have to do along the way. And it's something that, I don't know, I didn't find very satisfying. I don't know how you guys felt about it. So here I'm just highlighting those different equations for you. All right, so how do we work this out? So you might think you have to work this out using the Hamilton equations of motion. That's what Born and Jordan did, but you really don't. You just have to use the definition of momentum, which is mx dot, right? X dot is p over m. And then p dot is the force, which is minus m omega squared x. And now what you do is you come up with an ansatz. You say, we want to decouple these differential equations by choosing a linear combination of x and p, where this alpha is going to be chosen so that a dot is a number times a. So this, if I can do that, then the differential equation goes from a second order differential equation to two first order differential equations. And we're going to, and this is the ansatz that we're going to take. We're going to say, can we actually set things up in such a way that we can do this? So you just plug into the differential equation. You take a dot is alpha x dot plus p dot. We then substitute in for x dot and p dot from these equations. You get alpha p over m minus m omega squared x. Now look at this. This has a coefficient that's just p. If it's going to be a number times a, the coefficient is going to have to be alpha over m. So you immediately learn that c is alpha over m. And then because I know what c is, I can determine what alpha is from this coefficient, because this coefficient in the second half of the equation will be c times alpha. So c times alpha is minus m omega squared. And you see, these are algebraic equations. So we now want to solve them. So we plug in for c into this equation. We get alpha squared over m is equal to minus m omega squared. We solve for alpha. You see, alpha squared is minus m omega squared. So you're forced into picking an imaginary number for alpha in order to make this work. And the c is plus or minus I omega. There are two solutions, but now it's trivial to solve. A dot is minus I omega a. That means a is a0 e to the minus I omega t, where a0 is just the initial value of this, which is p0 minus I m omega x0. You can do the same thing for the a dagger or the a star. A star is then p plus I m omega x. It satisfies the differential equation with a plus I omega. And so a star is a0 star e to the I omega t, where a0 star is p plus I m omega x0. Okay, now we have these two equations, one for a and one for a star. How do I get x? I just solve these two equations for x. So x is just minus a plus a star over 2 im omega, and it comes out to be what you know it is. x0 cos omega t plus p0 over m omega sine omega t. Okay, so the key thing about this is that the complex numbers arise naturally from the way that you're solving the equation. They're not something you have to put in by hand in any fashion. You just have to try to do this ansatz that you want a dot equal to c times a. Now, I'll just have a little bit of a comment. If you study differential equations, coupled first order differential equations have a matrix structure. And the way that you solve the coupled differential equation is you find the eigenvalues and eigenvectors of that matrix. And that's essentially what we're doing here. It's just, we don't have to introduce matrices. We don't have to talk about eigenvalues. We don't have to talk about eigenvectors. We can simply ask, can I find an A of this form and force it to satisfy this equation? Okay. Any questions on this?
Yes, I have a question, Jim. Why did you take these ansatz? I mean, how do you know this form?
So that is a little bit harder to motivate. It's just something that we think to try to see whether we can make it work. You know, we're trying to solve these differential equations. And, you know, if there weren't differential equations and we were trying to solve this, you know, you're going to take linear combinations of these things to find the solution. So taking a linear combination, you know, it's not that far away from what you would do for solving ordinary coupled linear equations. but it is an ansatz. We're going to say, can we make this work? Okay, I don't have a better way of doing that, but if someone does, I would certainly like to hear it. All right, so the complex numbers are introduced naturally in the process of finding a first order differential equation. And there's a lot of interesting things from this. So we found A is A0 e to the minus I omega t, where A0 is P0 minus I m omega x0. And A star is A0 star e to the I omega t, where A0 star is P0 plus I m omega x0. So you can see if I take the product of A with A star, that's going to be time independent. If I multiply 1 over 2m times A star A, it's 1 over 2m times the modulus of A0 squared, which is P0 squared over 2m plus 1/2 m omega squared x0 squared. That is a constant. And you can see that's the total energy. But if I write the A back as P of t minus I m omega x of t, you see when I form this, I'm going to get the energy as a function of time. So the energy is conserved automatically in this approach, and it's very easy to see that energy is conserved. I think that this is really quite nice. Furthermore, we essentially showed that A star A was related to the energy. If you want to take it into quantum mechanics, if you raise these things into operators using commutator of x with p as IH bar, you can then calculate 1 over 2m A dagger A. You find that you have to add plus a 1/2 h bar omega, and that's equal to the Hamiltonian. So these things that we constructed as a convenience to solve the problem end up being the raising and lowering operators in quantum mechanics. So it actually provides a nice way of making a transition to quantum mechanics as well, if you teach the harmonic oscillator this way. So we can now look at the damped harmonic oscillator. For the damped harmonic oscillator, we have an extra force proportional to the velocity. We're just taking a velocity-dependent force as opposed to a square of a velocity-dependent force. And again, we pick A as alpha x plus p, and we want to decouple the equation such that A dot equals CA. We just do the same thing. We differentiate it, substitute in for x dot and p dot, and we then match coefficients. So this is the coefficient of p, that must equal c. And then this is the coefficient of the x term, that must equal c alpha. We then take this for c, plug it into here, solve for alpha. It's a quadratic equation, and the solution is gamma over 2 plus or minus 1/2 gamma squared minus 4 m squared omega squared. We're going to work in the underdamped regime where gamma squared is smaller in magnitude than 4m omega squared, 4m squared omega squared. So this is a pure imaginary number. And this is what the C is. So now we have our differential equation. The A takes this form now, and the A dot has this thing. This is just a number. So this is, again, a very simple exponential differential equation, so you can immediately solve it. And it's going to give us the standard damped solution. We would have a similar solution for the A star, and we can combine them together again to get the x of t and so forth. And everything works out exactly the way that you know that it does. For the driven damped harmonic oscillator, we now have an extra term that's an f of t. That makes this into an inhomogeneous first order differential equation. And it's easy to show how you can solve this inhomogeneous differential equation by using an integrating factor. In this particular talk, I'm not going to have enough time to go into those details in full. So for me, I find this to be a much more natural way to introduce complex numbers. And I think this added connection to quantum mechanics is really cool. And that's another bonus of doing things this way. As I mentioned at the beginning, we aren't the first people to think of this. It actually, as far as I can tell, goes back to 1930, but there has been more recent work. This person, Gauthier, essentially discussed this method of solution, but he didn't talk about doing it as a way of introducing the complex numbers in a more natural way. There's this paper from American Journal of Physics, which emphasizes solving these equations in the standard coupled first order linear differential equations way using matrices and eigenvalues and eigenvectors, which I think is too much for freshmen. I don't think they're going to be able to follow that. This paper is a little bit of a critique of Gauthier's paper. He tries to say there's an even better way. I mean, he comes up with essentially the exact same approach, but he says there's a better way of motivating it. And this connection between the classical harmonic oscillator and the quantum oscillator, again, I would say it goes back to Born and Jordan, but there's a recent paper by Alves that also has rediscovered this connection. Okay, now what's really interesting is these ideas can be extended to Kepler orbits and linked to the quantum solutions of hydrogen. And of course, in this talk, I won't have enough time to talk about it because it's only like a 10 or 12-minute talk, something like that. So I'm going to actually give that talk in the fall meeting of the CSAAPT. And that is all I have. This is work done with Leanne and Jason. And we have support from the Air Force Office of Scientific Research. And of course, I always have to put the McDevitt's on everything I do because they pay my salary. All right, questions or comments from anyone?
Just one question. So there is also, when one learns about these electronic circuits with AC current, I think
Yep, there is also works for LRC circuits.
Yeah, so that's what I wanted to ask. Like, if you have
it also works exactly for LRC circuits. It's just there we don't have a connection to quantum mechanics, but it will work for LRC circuits just the same as it does here. Yeah.
Okay. Yeah.
And in fact, in instruction, in some cases, textbooks are not so willing to talk about the complex numbers in a freshman class. What they do is they just don't introduce complex numbers. So you have to they just say, here's an ansatz, e to the minus gamma over 2t, times a cosine of some omega t, and we don't know exactly what it is, plug it in and we're going to solve for the gamma and the omega kind of a thing. It's very unnatural, the way that it is introduced. It might be in those same textbooks when they get to the LRC circuits, they do it with the complex numbers. But I think there is some movement within the freshman level textbooks not to have complex numbers in them. At least that's what Jason and Leanne and I found when we looked at a number of freshman books. They just don't want to put complex numbers in. Of course, Feynman had no problem doing that. He's teaching to both freshmen and sophomores, and he's teaching at Caltech. So they can manage doing complex numbers without him being bothered by it. So it might be that, well, I don't know. I mean, I don't know whether those kinds of circuits get covered in a junior level electrodynamics class. So it might be that most physics students don't actually see the complex number way of doing LRC circuits, which is kind of a shame if that's the case. Unless they take a differential equations class where it would almost certainly be something that they would see. Other comments or questions? I'm curious, Kyla, since you're the Omer is here too, Kyla and Omer. Have you seen this in your classes? Not the way I did it, but have you seen the introducing complex numbers to do damped harmonic oscillator? And did you like the way that it was done, or have you not seen it?
I don't think I've seen it, but I also haven't taken too many upper level courses. So,
well, I'm thinking more about in terms of like the freshman course, whether it was covered there. But I'm guessing not.
No, it wasn't.
It seems to be that there's but did you do a damped harmonic oscillator, or you didn't even cover that?
I think we did. I think we did do a damped harmonic oscillator. I can't remember if it was in that course. But maybe it was actually in our like classical mechanics course, so it wasn't quantum that we were working.
It's actually common to do it in the classical mechanics class, but there I would suspect you did it with the complex numbers if it was the junior level class.
We might have. I just remember doing a lot of algebra for it.
Were you happy with the way it was done?
I didn't love it.
Mm-hmm. All right, Omer, take care. That means we
Looking back,
lost
I
the
think I
rest
had to
of our.
memorize. I think I had to memorize some, like for the exam, I think I had to memorize quite a bit of things for the damped harmonic oscillator.
Like what the
And sometimes when you
was or
memorize, you
something
like,
that.
yeah, it like leaves your brain afterwards.
Yeah. Yeah. How about you other guys? I actually saw it as a freshman. I know for sure I saw it as a freshman. And I was very troubled by it. How is this done in Ukraine, Oleg? Did you cover this or do you not remember?
I actually don't remember, but I'm trying to memorize when we are introduced to complex numbers.
In your curriculum?
Yes, it's definitely not in high school. It starts as a freshman, but I'm not sure if it was in first semester or second semester, and it is definitely was from our mathematical analysis. We have different courses, and it was kind of in parallel. So when we learned about complex numbers from mathematical perspective, we didn't know why we are supposed to learn about that, when we're gonna use it, and then it was later that for sure we've been introduced with complex numbers in theoretical mechanics, but that's exact point I just missed. Yeah.
How about you, Marco? Do you remember for yourself when it came out?
I went to physics competition in high school, so it's not taught in the regular high school classes, but there were some problems for the physics Olympics, which were regarding the LC circuits, and they have this trick where they introduce that the current is a complex number, and then you do the computation, then take the real part. But that wasn't the part of a regular high school curriculum.
Yeah, but they did it this way. Just do the calculation with complex numbers and take the real part at the end without really properly explaining.
So that was maybe the last year of the high school, and then there was like a freshman course in classical mechanics, and I think that's where we did it in the first year.
Yeah. So how about U.S. instruction? Logan, Ryan, Jason, and Jeremy? Well, Jeremy, you were at Georgetown, but if you have any comments, you can.
I definitely did not see it as a freshman. I think maybe in analytical mechanics is the first time I encountered it. And
yeah, I found that it is in Marion and Thornton. So if you're using Marion and Thornton, it's definitely there. There's like a new book by Taylor, I think, or something. That's becoming a
actually, I used
book. I haven't looked into that book.
The first time I definitively remember looking at it is in grad school in our computational course. And in that, it was definitely presented as, oh, you just do this and then take the real part.
Yeah. How about you, Logan?
I think I've never done it in a physics class in my undergrad, but my PDE class, there's a
differential equations class almost certainly will cover this.
But I don't remember my math professor ever said something like on the line of take the real part, because I think to them imaginary number is just a very bad name, because imaginary numbers to them are real. I mean real.
I know what you're saying. It's they don't care about the physical constraints of a position having to be a real number, so that it doesn't bother them. How about you, Jeremy?
Yeah, we definitely did driven damped in the upper level classical mechanics. I don't remember exactly how we did it, but I don't think it was the way you're showing. So I'm imagining it was the take the real part solution. And then, I mean, we did it I think like Ryan said, in computational, but that was just using, differential equation coding. So
yeah. How about you, Azadeh? What is it like in Iran?
I didn't see the way that you just showed in quantum mechanics, but I think the first time I saw it in math, or as Ryan said, in analytical mechanics. Yeah.
So in the more advanced classical mechanics class, not the first one.
No, the first one.
Oh, in the first one. Okay.
Yes. Mm-hmm.
Yeah, that's not shocking. Iran, I think, is okay throwing the more complicated math at their students. They, just like a lot of places in Europe, tend to do this as well.
Mm-hmm.
Jason, how about you? Did you cover this or no?
I'm pretty sure I did cover in my freshman level physics 1 class a basic version. The weird thing with Temple University, where I took it, is that physics majors took the algebra based courses because we were taking calculus concurrently, like in the normal track. So they don't expect that any calculus at all. So it's all algebraic.
So there was no differential equations or anything like that.
That is correct. They basically gloss over all differential equations in that class. So they definitely, like, I know I did it, so I don't remember how I did it, but they must have super glossed over any type of.
They must have just said what the answer is. I mean, there's no way that you can, if you're not going to take a derivative, you can't do that.
That's correct. And then sophomore level, we took classical mechanics by Taylor, and that definitely had some version of using complex numbers, but I don't remember if there was a good explanation after that. I feel like they definitely just took the real answer only for Taylor as well.
Okay. All right. Well, that's really all that I have. Thanks everyone for sharing what your experiences are. I mean, anyone have any opinions on this? Did you like it, or was it as bad as the way that you did it before? I didn't have a chance to tell you about how this works for orbits, but it's actually quite interesting for orbits. It might be the easiest way of getting the orbit equation. It's really very, very direct, very nice. And again, there's a connection to quantum mechanics. So the thing that you work out is if you change everything into operators, it is the operator that you have to work with in quantum mechanics. And, similar to harmonic oscillator, where the quantum mechanics has this quantum correction, where it's not 1/2m A star A, it's 1/2m A dagger A plus 1/2 H bar omega. The hydrogen problem, the classical one, has an L squared over 2m R squared in it. But if you work it out with operators, it becomes L times L plus 1 over 2m H bar, 2m R squared. And of course, you also get a factor of H bar because now the L's are integers as opposed to the angular momentum. But everything else is the same. So it's really, it's quite fascinating, I think, how nice and simple this works. I think it also allows you to get the orbits of harmonic oscillator central force, but we haven't worked out the details for that.